function of conversion, and this as a function of conversion, and then we'll have the concentration. So let's start, and we're going to leave F in for the time being. Fj over now V naught times Ft over Ft naught times P naught over P. You guys remember that? That's what volumetric flow rate's equal to, right? I've gotten rid of the compressibility factors, but I've left it in terms of the flow rates, and now we're going to get rid of the flow rates. Some of them anyways.
Is it not isothermal anymore?
No. Obviously, you can say at any point that it's isothermal, and that drops out. But no, when I wrote that, the pressure wasn't changing, the temperature wasn't changing. That wasn't like forever. That'd be nice though. And this we can define as the total concentration of inlet species, right? Just Ft over V naught. So since those are both properties of the inlet, we can do that without any issues. And then we still get the rest of this. Fj over Ft, P over P naught, T naught over T. So this isn't what we wanted, but I'm writing it on the board for a reason. It's not in terms of conversion, it's only in terms of the flow rates of the species. So is there a time when we might not want to put things just in terms of a single conversion?
You have multiple reactions.
When you have multiple reactions. Use this equation right there. When you've got multiple reactions. It's more convenient to solve everything in terms of the flow rates than it is to try to solve every flow rate in terms of two conversions. Again, that's for flow reactors. Yeah?
Why is the initial pressure in the denominator and the temperature in the numerator?
Are they on the same side? That's why. It comes out of that. All right, but now let's say we don't have multiple reactions, so we actually want to get things in terms of conversion. We had a table up here that had Fj as a function of big theta, right? Fa naught, conversion, all that. That's what we're going to pull back now. And I can do a little bit more simplification. One, I can recognize that what is this? That's just the initial concentration of A, right? And we had an expression for everything down here. or excuse me, we have an expression for this. Ft over Ft naught is just that. 1 plus epsilon times conversion. And these are still here. But now I'm going to flip them over just because I'm pulling them out of the denominator. Hell, screw that up. So you got me thinking about it, and then I put them on the same side. And what is V in the numerator here? What is this guy? Yeah, just to remind you. But that saves me from having to write 4 reactions, 4 equations for A, B, C, D, right? All right, so finally, we now have C as a function of X. And unlike before when we wrote it on the board, now nothing else is changing, right, with X, except maybe temperature. So these, as a function of X, will come later.
Dr. Booth?
Yeah.
This is only for a single reaction, correct?
Yes. Because again, I mean, where's the second X, right? So this is for a single reaction in a flow reactor. Flow reactor, because you see that these are all volumetric flow rates, right? So what this exercise maybe has shown you, maybe hasn't, the concentration is changing for 2 reasons, right? What are they? Conversion and dilution, volume change, right? Volume change. So it only really matters if, if A goes to B, then what's true?
A decreases, B increases.
Delta is equal to 0. That means epsilon is equal to 0. That means this whole thing cancels out, right? And we had that on the board earlier today. Because those volumes cancel out, and that's why you end up with just the concentration terms and nothing else. So we wrote that on the board whenever the volume was constant. That's true if the volume's constant, or if, well, I should say, if you're going A to B, then that also means the volume's constant, right? So this just drops out. All right, let's do an example. There's a lot of stuff. Hopefully putting some numbers on the board will be helpful. All right, we've got a flow reactor. Got it. questions from just the problem statement?
Does that say 28 mole percent?
Yeah. I mean, it would say that if I finished writing the work. So, how much air, sorry. I know the inlet mole fraction of SO2. What's the inlet mole fraction of O2?
You have to convert it
Right, everybody got that? What is it?
100 times 70.
0.21 times 0.72.
Do we take a basis?
So everybody knows where he got that, right? 72% air. Air is 21% O2. So that is 0.151 O2. So should I divide this reaction by 2? Why? What if I would have written O2 plus 2SO2 goes to 2SO3? Then would you have told me to divide by 2? Okay.
It depends on your limiting reagent, right?
It depends on your limiting reagent. Yeah, we haven't talked about this yet. I thought it would make more sense with an example instead of like A's and B's and that junk. What you want to have a 1, you know, the question is, do I divide by 2 and then SO2 will have a 1, or do I divide by nothing, right? Divide by 1, and O2 will have a 1. What you want to choose, limiting reagent as basis. Why?
Once there's no more of it, it won't convert.
Yeah, that way your conversion, the maximum conversion you can have is 1, right?
You'd have negative coefficients the other way, wouldn't you?
You would have negative coefficients, but if it's not limiting, then the maximum conversion, you stop maybe at a conversion like 0.5 or something, right? Because you got no more A, so you can't react with it if you're B. So no, the basis that you want to choose is whatever your limiting reagent is. That's what you choose as your basis. Which one is my limiting reagent? How do I evaluate that?
Multiply O2 by 2. Which one's greater? Or which one's less? Since for every 2 SO2, you have an O2.
Right, I multiply O2, this concentration, right, by 2,
Yeah.
and what do you get?
0.3, it's more than SO2.
0.3, which is more than SO2. So now I'll ask the question, should I divide by 2? Yes. That is because SO2 is limiting. So that's the first thing you want to do in these problems.
Wait, why do you multiply that by 2?
Because if I have, imagine that you have a basis of 100 moles. That means you have 28 moles of SO2. How many of those do you need? How many moles of oxygen do you need to react 28 moles of SO2?
14.
Right. You need 14, right? From the stoichiometry, 2 to 1. And I've got more than 14. I've got 15.1. So when I go to complete conversion, I'll be out of SO2, and I'll have just a small amount of O2 left over. So yeah, SO2 is limiting. And again, that's the first thing you want to figure out when you've got one of these problems. Unless you're lucky and it's like both of these coefficients are 1. But how often do you guys think you're going to be lucky?
How nice
All
are you
the
feeling?
time, right? Yeah. All right, so I rewrite it. If it helps you, I do not have a problem if at this point you do something like this. Okay? That's not going to bother me, because sometimes it's annoying to put FSO2 inlet, FSO3 inlet, and it's hard to read those, right? So it's fine if you want to do that. If you just put that and then that right next to each other, I get it. You don't have to like write me a 1.5-page long explanation of what you're doing. But that just means from then on out, you can use things like FA, FB, FC. Okay? Is that clear with everybody? All right, and I think I'm going to do that because that's how the notes are done. Okay, so what are my inlet conditions? Right? That clear?
Since it doesn't state it for simplification purposes, couldn't you just define a basis like as one, so that way you don't have to write FT not continuously over and over and over again?
Generally speaking, you might be able to define a basis, but I don't think that you can here.
Okay.
Because I gave you some other information that I think will show up and allow you to calculate FT naught.
Oh, because of pressure and temperature. Yeah. Never mind.
Okay, but yeah, FB naught is equal to what? 0.21. I mean, we already did the math, but we'll put it out in its entirety. What's this? 0, yeah. Unless you're told that some of the product is in the feed or there's a recycle or something, then even if it's not in the problem statement explicitly stated, you can assume that there's no product fed to the reactor. Again, that's not always going to be the case. Sometimes you'll have a recycle stream. Sometimes I might just say there's some product being fed. Then what inert do I have in the system?
0.79 times 0.72.
Yeah, we call that nitrogen. I can go ahead and write that, right? The flow rate of the inert is always the same as the inlet flow rate of the inert. It doesn't change with conversion. That's why it's inert. So I've written this in terms of total flow rate. Is that normally how we want to write these, though, if we want to set up one of these stoichiometric tables? No, right? We want to write everything in terms of this. So let's write out the stoichiometric table. And first, let's go ahead and define theta B. Right? So you guys see that the total flow rates cancel out. So you can just, if you have this, all you have to do is look at the ratio of the mole fractions. What's theta C equal to?
0.
0. No initial flow rate, theta is going to be equal to 0.